Okay, welcome to your second video lecture in section 10.2 on Fourier series. Okay, so to determine the coefficients a(n) and b(n) for this Fourier series here, okay, of a given function f, we first, as sort of a backwards way of logically going through this, we first suppose that the series above actually converges to f, and we'll discuss in a subsequent lecture what's necessary for that to actually be true. If this is the case, then f can be represented as this series. Okay. And what we're going to do is use the orthogonality conditions of these Fourier basis functions to find each of the a(n)s and b(n)s individually. Okay, so first, to find the a(n)s, what we'll do is multiply both sides of this expression here, this equation, by the nth cosine Fourier basis function, and then integrate from negative L to L. So if we do so, what we're going to get is the inner product of f with the nth cosine Fourier basis function. Okay, and because the inner product is linear, we'll be able to take each of these guys here, and then also the first coefficient, and when we multiply by cosine of n pi x over L and integrate, we're just going to get the inner products of these terms here. Okay, and we know from a previous lecture that all of those inner products are going to be 0 except for the one where both n and m are the same and the trig functions are the same. So namely, all of these are going to go away except for the nth term, which is going to be the inner product of cosine of n pi x over L with cosine of n pi x over L, which we know from a previous lecture is L. Okay, the coefficient, of course, with that term does not go away, it's a(n). And thus, a(n) is literally just, if we divide both sides by L, the inner product of f with the nth cosine Fourier basis function divided by L, which, as we expand by definition, is just the integral from minus L to L of f with cosine of n pi x over L dx divided by L. And if we do a similar thing by multiplying by the nth sine Fourier basis function, we'll get this expression for bn here. And so once we have the a(n) and the bn, we have the Fourier series for f in the event that it actually converges to f. And so we can write that down using these integrals. Okay, so for example, let's look at this function here, f, which is negative 1 when x is between negative 2 and 0, and 1 when x is between 0 and 2. And then it's 4 periodic. So in other words, if we draw this guy, what we're going to have is a function that's 1, and then negative 1, then 1, and so it continues to repeat itself in this piecewise continuous way. At 0 it's 1, so there's a hole there, and then a hole there, and filled in there, and so forth. Okay. And in this case, it follows that if you look at the a(n)s, which is just 1 over L, which is 2, integral from negative L to L, which is the integral from negative 2 to 2, of f times cosine. You could split this into two integrals, and after a little computation, you find that the a(n)s are 0, actually. If we look at the b(n)s, again, it's just 1 over L, integral from negative L to L, of f times sine, split it into two integrals. You end up with this expression, which is 0 when n is even, and 4 over n pi when n is odd. And so, thus we only have a bunch of odd sine terms in our Fourier series there. Okay, so you can write n as being odd as 2m minus 1, where m is a positive integer. Okay. So how does this perform? Well, if we just take the first two terms of the Fourier series, it doesn't perform well at all. If we take the 4 terms, it starts to perform better, and all the way until we get to 16 terms, it looks like it performs okay. Again, you have some wiggle here because of the sine functions in the approximation. What's interesting here is that sines and cosines are all continuous, so somehow it has to resolve this discontinuity here and here and here. And what we'll find in the next lecture is that it basically just takes the average over the discontinuity. Okay, thank you.